3.2 Properties of Solids. Introduction. Unit 3.2 of AP Chemistry explores the properties of solids, including their structure, bonding, and physical characteristics. Different types of solids, such as ionic, molecular, covalent network, and metallic, exhibit unique properties based on the forces holding their particles together. Understanding these properties helps explain metallic behavior and applications in real-world chemistry. Solids intro. There are four different types of solids: ionic, metallic, molecular, and covalent network. Ionic solids are held together by electrostatic forces between cations and anions. Metallic solids are held together by metallic bonds between atoms. Molecular solids are held together by weak IMFs, and covalent network solids are held together by an extended network of covalent bonds. Ionic solids. Ionic solids have ions at the points of lattice that describe the structure of the solid. Due to strong interactions between ionic solids tend to have low vapor pressure, high melting points, and high boiling points. The attraction between the positive and negative ions is known as an electrostatic attraction and can be described by Coulomb's law. According to Coulomb's law, smaller ions and/or ions with higher charges will have a stronger attraction between the ions, resulting in higher lattice energy values. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. They conduct electricity only when the ions are mobile or when the ionic solid is melted or dissolved in water or another solvent. There are generally between a metal cation and a non-metal anion, though there are some non-metal cations. Metallic solids. Metallic solids consist of metallic crystals with spherical metal atoms packed together and bonded to each other equally in all directions. A metallic bond is considered to be a closely packed lattice of positive atoms/ions surrounded by a sea of moving electrons. The movement of the electrons causes metals to be good conductors of heat and electricity. The close packed atoms/ions allow for metals to be malleable and ductile due to the ease with which the metal atoms/ions can be rearranged in structure. The image to the right shows a metallic solid with a sea of valence electrons. Molecular solid. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak IMFs. The molecules used to form molecular solids are, by definition, composed of nonmetal atoms covalently bonded together. Molecular solids generally have a low melting point because of the relatively weak IMFs present between the molecules. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds and lone pairs of each consecutive molecule. Molecular solids are sometimes composed of very large molecules or polymers. Covalent networks. Covalent network solids have atoms at the lattice point with strong directional covalent bonds to form a solid that might best be viewed as a giant molecule. These are only formed from nonmetals, elements such as diamond graphite, or binary compounds of two nonmetals such as silicon dioxide or silicon carbide. Types of atoms seen at lattice points in covalent network solids are carbon, diamond and graphite, silicon dioxide, silicon carbide, and other non-metal combinations with B or GE. To melt covalent network solids, covalent bonds must be broken. Because covalent bonds are relatively strong, covalent network solids are typically characterized by hardness, strength, and high melting points. Three-dimensional network solids are also rigid and hard because the covalent angles are fixed. On the image to the right, there's a diagram of covalent networks. Extra knowledge. Metal alloys. Metal alloys are a type of mixture. There are two main types of alloys: substitutional alloys and interstitial alloys. More about those on the next slide. Biomolecules and polymers. In large biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape of the molecule, which is largely dictated by non-covalent interactions. Metal alloys. Alloys keep a sea of electrons, so they will still conduct. Some alloys form a chemically inner oxide layer on the surface which protects them from rust. Substitutional alloys. An atom of similar size substitutes for another atom in lattice. Since the atoms have similar radii, the density of the alloy falls between the density of the two metals. Alloy remains malleable and ductile. An example of that is shown on the image to the right, specifically the image to the top. Interstitial alloys. A smaller atom fills the gaps between larger atoms. Specifically, since the atoms have different radii, the interstitial atoms tend to make the lattice more rigid, decreasing malleability and ductility, but making the alloy stronger. An example of this is shown on the right to the bottom. Example problem. Of the following diagrams, which best represents the structure K and F? And the answer is B. And the explanation is, since K and F have similar radii size, they will form a substitutional alloy, which is shown in answer choice B. To determine radii size, you must look at the periodic table and look at the trends on the periodic table. Some extra videos are these two listed below. They will help you learn more about alloys and metals and metallic bonds.